Hello everyone. I know I haven't posted a video in a while, and that's just because I've been busy with graduate school and everything that comes with it. And currently, I'm working on giving this talk pretty soon, and I want to do a video just going through my talk. Number one, to practice. Number two, maybe get feedback from you guys. So if you have any suggestions on my presentation or how I can improve it, leave it in the comments. And then number three, I actually have a Q&A session I'm doing right after I give this talk about my presentation. So I'd appreciate any questions you guys have if you could leave them in the comments. That way I can kind of anticipate what might be asked of me. Okay, so with that, I'll get started. So my talk is on evolution of the universe and modified loop quantum cosmology. And I'm just going to give a quick outline of what will be discussed here. So we're going to start by talking about gravity, talking about quantum field theory, and talking about some problems when you try to combine the two. Then we're going to present a solution to this problem in the form of loop quantum gravity. We'll talk a little bit about what that is, and we'll also talk about the implications of what the theory says, what it means, and how we can apply it to a particular situation. With that, we can get an effective Hamiltonian, and with the effective Hamiltonian, we can attain what's known as the Friedmann equations. Those equations will be very helpful because it'll let us find things such as the expansion rate of the universe. And that'll be based off of, as well as the equation of state of the universe. And that'll be based off of potentials of something called the inflation field, which is the cause of the expansion of the universe. So for these different potentials in the inflation field, we can see what the equation of state looks like. We can talk about the expansion rate, and we can discuss those sort of things. So let's start with talking a little bit about, we'll start with general relativity. I want to talk about all three things in the subtitle here. But we'll start with general relativity. So general relativity was given to us by Einstein in the year 1915. And it is one of the most successful, well-established theories in all of physics. General relativity describes gravity as a curvature of space-time that is caused by mass and energy. So GR has been confirmed through different experimental tests, different observations, and it's been very reliable. A couple examples are it's used to better understand orbital mechanics. I think there will be some talks that discuss that in greater detail going forward. It also predicts things such as gravitational lensing. Gravitational lensing is where light bends around these big objects. And when I say big, I'm talking on the order of galaxies. Bend around these massive objects, or black holes, for example. Black holes are another prediction that come out of general relativity, which we now have, we've had evidence for a long time of them, but we actually recently had that image of a black hole. What was it, like 5 years ago or something along those lines. Gravitational waves have been detected by LIGO, which is another successful prediction of general relativity. And it's been used in industry in applications with industry, such as GPS. It's the GPS system. And if you're like me, you probably won't even make it home tonight without GPS. So, thank you, Einstein. But we have a second theory as well. We have quantum field theory, which is another very successful theory in the realm of physics. And it's really the building block, it's the foundation of the standard model of physics. And this describes three of our fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. Notice I've left gravity out of that list. We'll talk about that in a second. This has also been a very successful theory. It's explained stuff like quarks and why quarks, you'll never be able to separate them because the energy required to do so would just create another one. So you'll never have these isolated quarks. It's been used to describe things such as the magnetic moment of an electron to very high precisions. We've had the discovery of the Higgs boson in 2012. So we've had just success after success with quantum field theory, and unfortunately we're not able to combine the two. And what I mean by that is general relativity is not normalizable. So what do I mean by that? Those three other forces that I mentioned, the electromagnetic force, the weak nuclear force, and the strong nuclear force, there's a process known as renormalization in quantum field theory. Basically, this deals with infinities that pop up when we try to calculate physical quantities, and as a result, these quantities aren't really physical. So there's a way we can renormalize this and manipulate the math a little bit to where these infinities cancel out. And then we're left with something finite. We're left with something that has physical meaning. So we've been able to do this with all of the three out of the four forces. But when we attempt to apply renormalization to gravity, treating it as a quantum field, it just doesn't work. The infinities do not cancel. So when that method that we apply doesn't work, we can say that we need basically a quantum theory of gravity if we want to bring these together and really have a more complete theory of gravity. Now, you might ask, why do we really need it? I mean, I guess it would be great if we could unify them, but there are situations where we really need a quantum theory of gravity if we want to discuss certain situations. And one clear example of that is, well, I have the Big Bang here, but we'll talk about maybe an alternative way to think about it. We would need a quantum theory of gravity when we're talking about extreme conditions like what was present during the Big Bang. The Big Bang being the moment when the universe was extremely hot. It was very dense, and the entire universe would have been on the scale of the Planck length, essentially immediately after expansion. And at that scale, quantum effects are going to dominate. Essentially, the whole universe you could think of as being a quantum universe at that point. So if you want to talk about the universe at that point, you have to include quantum gravity. There's no real way around that. So there's a lot of different theories that give us some quantum theory of gravity. There's string theory, there's supergravity. There's a few different theories out there, but this one is going to focus on what's known as loop quantum gravity. And in this case, modified loop quantum gravity, which is it's important to know what loop quantum gravity is first. So what loop quantum gravity does, the main idea is we no longer think of space-time as this smooth, continuous fabric like we do when we're considering it from a general relativity point of view. Instead, we think of it as having discrete units of length. And in a sense, you could think of it as quantizing space-time itself, or quantizing general relativity. Just as we quantize energy for maybe a quantum simple harmonic oscillator, or we quantize angular momentum for electrons, we maybe can also quantize space and time itself. So that's the idea behind loop quantum gravity. And you might ask how this changes how we think about maybe the Big Bang, for example, where we see some of these singularities pop up. And the way that it removes this is because there's a smallest unit of length, the smallest unit of volume, the universe never actually condenses into this infinitely dense state. Instead, it would condense down to the smallest possible volume, I suppose you could think of. And instead of a Big Bang, we instead think of this as a quantum bounce. So, before the Big Bang, we can think of the universe as being in this state of contracting. So the universe is getting smaller and smaller and smaller. And due to quantum effects at that very beginning, you see we have inflation at 10 to the minus 32 seconds. Even before that, we have the universe contracting to this very small point, and as it gets close to the Planck length, we have quantum effects. And the universe eventually bounces and is no longer, that's the point where the universe is no longer contracting down, but rather expanding. So we no longer have this infinite density, and we no longer have this infinitely dense point like we do with general relativity. Now, under this framework, we can actually think of moments before the quantum bounce, because what this is essentially telling us is the universe was contracting. So there was time you could think of before the bounce, and that's sometimes what people consider to be the beginning of time. But in this case, that wouldn't actually be the beginning. It would just be the time of the quantum bounce. Now, a big focus of this paper is the expansion of the universe. What exactly is driving this expansion? So when we look up and we see light from distant galaxies that are shifted towards the red end of the spectrum, that shows us that our universe is expanding. The cause of this is called the inflation field, which is considered a scalar field. There are some theories where it's something other than a scalar field, but it's a pretty common approach to take. So the scalar field, since it's a scalar field, there's some spin zero boson that represents this field, which we can think of as being an inflation particle. Now, this paper works very similarly to other papers that examine what the expansion of the equation of state for the universe is post-quantum bounce. And what these papers find is if the kinetic energy is overwhelming the potential energy, then the potential energy of the scalar field usually doesn't really change anything in the long run. But again, these papers looked at time after the quantum big bounce, which is where you can avoid a lot of these singularities. But with loop quantum gravity, we no longer have to worry about those singularities, and we can look at the time during the bounce and even before the quantum bounce. So that's something new that this paper adds to the field. And you cannot see my equations there, which is unfortunate. I don't know why. I need to fix that before I give the talk. But essentially what we will have here is what's known as the equation of state. We'll talk about that in a second. So we're going to start with an effective Hamiltonian. And I do have that actually way down here. We have our effective Hamiltonian at the very bottom there. And Hm is a function of potential. And from the Hamilton's equation, we can use these to find, so you get Hamilton's equations from that. And then we can use that to get our FR equations, our Friedmann equations. And we can find things such as the expansion rate, or the expansion factor, that again depend on the potential energy. And then, of course, our equation of state, which you can't see here, but our equation of state is our, P over rho, where it is our density in energy over density, I believe it is. And we can examine those as well. Now, the first potential we're going to consider is what's known as the chaotic potential, which is given as 1/2 m² phi². Now, in this case, phi and its derivatives are invariant under a parity transformation. So because of this, it doesn't really matter what we pick as our initial condition, whether it's positive or negative. The expansion factor will take care of that, and it'll still be positive. So the equation of state you can see on the left here, and you can roughly break this up into three sections. You have the first section, which is where the equation of state is equal to about -1. This is what's known as the pre-bounce region. Now on the right-hand side, so if you go to we're on the left part of it, now the right part of the graph where it's kind of flat, that's known as the pre-de Sitter space phase. And in between those two regions where our equation of state fluctuates between positive and -1, that's known as the pre-transition phase. Now, for all the potentials looked at, you'll see those same three phases pop up. They might look a little different, they might be moved a little bit, but we'll see those same three phases pop up. And in fact, when we consider the equation of state for a time positive, that's to say a time after the quantum bounce, we see a pretty similar result. We have these three phases. They're the same phases that we talked about here, but they're no longer pre. So we just have the de Sitter space phase, the transition phase, so on. But they follow the same pattern. And then over here, so another equation that's not shown here because it's cut out, is this n value, which is essentially the log of the ratio of our expansion rate, which gives us an idea of the expansion rate of the universe, just kind of like in a log scale. So we have this here, and you can see basically how quickly the universe is expanding once it reaches certain points. So that is the chaotic potential. The Starobinitsky potential. Again, I have to fix the potential because you can't see it. The graph did not really look as well when I downloaded it, but I have time to fix that. Regardless, pretend you couldn't see it. So this potential is a nice one to use because it's considered flat for large phi values. Now, mathematically, what this means is the derivative of our scalar potential is significantly less than the potential itself, which, in terms of cosmology, what this means is we get a mechanism that allows for rapid expansion of the universe. So this is a good potential of interest. I believe it pops up in GR a lot as well. So you can see the equation of state. In this case, it's worth considering two different times, pre and post bounce, because we don't have that same symmetry that we had with the chaotic potential. And we have different initial conditions for our phi of b as well that you can see. But regardless, we do get the same structure in terms of the three different states that we get, the three different phases, if you will. And we also get expansion rates depending on if we take our the derivative of phi to be positive or negative. And in both cases, just like with the chaotic potential and the Starobinitsky potential, we get something known as slow roll inflation, which gets us what we're looking for in terms of their expansion rate. And then naturally, there's a generalized Starobinitsky potential. You can kind of see that potential there, which is good. And it actually reduces down to our previous Starobinitsky potential for appropriate values of alpha and V naught. I don't remember what those values are, but it is, you can actually get back to the potential we just discussed. This is also a potential that pops up a lot in string theory and supergravity theories. So it's kind of interesting to take a look at and see what happens. These graphs again give us an idea of the expansion rate for these different potentials, and of course our equation of state. You might notice the equation of state at the top right, kind of a weird one at the end there. But in general, we do get these three phases that we've been getting with the other ones as well. The last potential I want to talk about is what's known as natural inflation potential. So the natural inflation potential is particularly interesting because it arrives from a lot of theoretical frameworks with kind of pseudo-Boseen's theories. It also has the same flatness of these other potentials that we discussed, which is something that we're looking for to match predictions. So this potential has a pretty simple cosine form for the most part, so it's not incredibly difficult to work with. We get slow roll inflation out of this, which can explain the rapid expansion that we have. And it's also used a lot in high energy physics concepts as well, such as symmetry breaking, and I believe is also used a little bit in string theory. So it has a lot of connections to these different theoretical frameworks. So it's a very compelling potential that's definitely worth studying. And here is the expansion rates. These definitely are the most interesting expansion rates, I think, just because of our potential. But you can see, even though it's very weird looking, we're getting an expansion rate that is quite high, which is what we're looking for. We do want rapid expansion. So even though this looks pretty different than our other ones, it doesn't look parabolic, it's still giving us this slow roll inflation that we're looking to see. Here are some references that I used in this talk. And just to recap before I end here, we basically want to understand the universe at just fractions of a second after the expansion. So in order to do that, we need a quantum theory of gravity. And loop quantum gravity is the theory that was used in this paper, in this talk. With loop quantum gravity, we can construct a modified Hamiltonian and obtain Hamilton's equations of motion. With these equations of motion, we can formulate the Friedmann's equations that can help give us things such as the expansion factor of the universe. Then with this, we can look at relative potentials for the inflation field, and we can find the equation of state and the expansion factor of the universe prior to the quantum bounce. So thank you for your time. If you have any questions, please drop them in the comments below, and I'll try to answer them.